Buddy, you're a boy, make a big noise playing in the street. Gonna be a big man someday. You got mud on your face, you big disgrace. Kicking your can all over the place, singing, we will rock you.
Greetings. This is Bradford Donald Keller Townsend, and this is a Forward Research Report. Sunday, October 7th, 2018. The title of today's video is Pure Mathematics is Psychedelic. I'd like to begin by reading some quotes. Psychedelic is an adjective of noting a mental state characterized by a profound sense of intensified sensory perception, sometimes accompanied by severe perceptual distortion and hallucinations, and by extreme feelings of either euphoria or despair. I'd like to read a quote from a textbook. I took a graduate course in linear algebra. The author of the textbook was Gilbert Strang. He's still a professor at MIT and has courses on the open course MIT that you can watch. Just to give you an idea of what math gets to be like at higher levels. We start with two-dimensional vectors and three-dimensional vectors, which are reasonable to draw. Then we move into higher dimensions. The really impressive feature of linear algebra is how smoothly it takes that step into n-dimensional space. Your mental picture stays completely correct, even if drawing a 10-dimensional vector is impossible. Then, from a topology textbook, our reason for approaching algebraic topology via homotopy is found in the strangely geometric flavor of the theory of homotopic mappings. Speaking intuitively, two mappings are homotopic if one can be deformed continuously into the other, or we may view homotopic mappings as being members of a one-parametric family of mappings with a continuous parameter. Since precision lies in this direction, we may begin with a general definition, which will be specialized to give the concept we desire. The book is titled Topology by John G. Hawking and Gail S. Young. Pure mathematics is one of the majors that people can select in college. Pure mathematics is math for math's sake, without thinking of potential applications. Many of the computer science mathematical tools, such as nodes, the theories of computational speed and logistics of trucking companies, there's so many different mathematical tools that are used. For example, Fourier transforms are used to compress television images and video games and superhero comic book films. Used mathematics that was not intended for that purpose, but people who enjoy math for math's sake because of its aesthetics or the beauty of math. Many people find mathematics relaxing. They see it, as a game or a pastime to be enjoyed, and math for math's sake. And the same arguments that I use for why be an applied math major. A subclass of applied math majors would be actuarial courses, and computer science is in the math department and is a subspecialty of mathematics. Pure mathematics would be attractive, I would think, if I was hiring for an advertising firm, any type where you want creative, intelligent people. There would be a use for pure mathematicians, especially in high finance, in computerized automated trading programs. There's two different approaches: the applied, where you're trying to solve practical problems, and developing math just because you like math and find it appealing. And so I think a pure math major and the courses you take, you would take topology, maybe more geometry, set theory, number theory type courses. While not obviously practical, that type of creative thinking is highly valued, and I think would lead to many interesting employment opportunities. That's all I have for now. Thank you very much and have a wonderful day.